I'm a professor in Japan, but here I'm just a student, and Kiao is my supervisor, not only my research work, but also the English. And today I would like to talk about the PBPK coupled modeling for inhalation exposure studies, but today I mainly focus on the exhalation exposure. This means the second-hand exposure in indoor environments. And I would like to start with this number, 100 microgram per cubic meter. This is the gas phase formaldehyde concentration criteria in indoor environments specified by WHO, World Health Organization, in indoor environments. And this concentration is defined as the time averaged concentration for 30 minutes in certain points in indoor environments. In accordance with the limitation of measurement method, sampling method, and analytical method. And I have a simple question. What is this 100 microgram per cubic meter concentration in indoor environments? Maybe you know that there is some strong heterogeneity, non-uniformity of flow pattern and concentration distribution in indoor environments. And this concentration, 100 microgram per cubic meter, is not consistent with the perfect mixing concentration in indoor environments, and not consistent with the inhaled air concentration, not consistent with exposure concentration, because of the, I would like to say again, non-uniformity of heterogeneity in indoor environmental quality. And this is one of the examples of our CFD simulation for targeting the very simple room model with standing human model with displacement ventilation systems. And you can see the clear thermal plume at the top of the human model. And this maximum velocity around here is 0.25 meter per sec. But in this room, the supply net velocity is just 0.1 meter per sec. And you can see the clear non-uniformity of a flow pattern. And in this room, I set the formaldehyde emission source here, floor, and therefore the non-uniform concentration distributions of formaldehyde generated in this room. And by using this CFD data, we can calculate the contribution ratio of inhaled air quality. And in these calculations, the approximately 70% of inhaled air were transported from the lower part of this room from the floor along with the thermal plume along the body surface, human body surfaces. And I would like to emphasize again we must consider about this heterogeneity, non-uniformity, to discuss about the inhalation exposure analysis. And this is the one more example of the discussion about the representative concentration in indoor environments. This is the result of the velocity distributions, and this is the formaldehyde concentration distributions. And in these simulations, perfect mixing concentration in this room is calculated to be 100 microgram per cubic meter. And on the other hand, the room averaged concentration, this volume average concentration in this room is calculated to be 91.1 microgram per cubic meter, just 10% lower compared to the perfect mixing concentration. This perfect mixing concentration is just calculated by the total amount of emission rate of formaldehyde divided by the ventilation rate. And furthermore, the breathing air concentration at nostril surface in this human model is calculated to be estimated to be 62.7 microgram per cubic meter. This is 40% lower compared to the perfect mixing concentration. And I would like to conclude here, of course, in indoor environmental design of indoor environment, we must pay attention to the perfect mixing concentration. It's a very simple and representative concentration, but we must carefully analyze the inhaled air concentration to discuss about the exact exposure situations. And this is one more examples of the distribution or partition of inhaled formaldehyde in respiratory tract. For the total amount of inhaled formaldehyde, in this case, is 82% of inhaled formaldehyde estimated to be adsorbed on the inner wall surfaces of respiratory tract, and 50% goes to the lower part of the airway, and 3% of inhaled formaldehyde estimated to be exhaled to the indoor environments. This means this 3% of inhaled formaldehyde will become a new emission source of indoor air pollution. And in our group, the overarching objective of our study is to develop the in silico human model for indoor environmental design to precisely analyze the inhaled air concentration. And here, in this presentation, I would like to introduce our current activities concerning the development of this in silico human model. And now we are trying to integrate PBPK model into this human model in addition to the thermo-regulation model to analyze the skin surface temperature distributions. And maybe someone will know about our PBPK model, and the PBPK is physiologically based pharmacokinetic model. And this model is objectives of this model is to estimate the health impact or the blood concentration of chemical compounds, something like that. And this PBPK model is basically described by the differential equations. For example, this is the very fundamental PBPK modeling, and this term is called as the Mucous-Menten kinetics. It's a non-linear term, and this one is the unimolecular reaction term with first order rate constant, and this is the diffusion term. These are the reaction term. This is the diffusion term. Therefore, mathematically, this formula is called as the reaction diffusion systems, and this is a simply differential equation system, and we can discretize this. And then these are integrated into the boundary, wall surface boundary condition of CFD simulations. And I'm not sure other research groups' activities, but in my understanding, the inner surface temperature distributions inside respiratory tract is not constant, not uniformly distributed, and then we must introduce some numerical model to reproduce the non-uniformity or surface temperature distributions and also the humidity distributions. And this is one of the examples of our current model to reproduce the inner to predict the inner temperature distributions in respiratory tract models. Furthermore, not only inside respiratory tract, but also in case of the human model, we must precisely analyze the skin surface temperature. And then this is one of the fundamental model to analyze the skin surface temperature distributions. And here, this is called as the two-node model, very simple model proposed by Gyagi, 1986. And this model solves the heat balance equation of human body in two regions, core region and skin regions. And by using these governing equations, we can estimate the core temperature deeper inside human body, and also the skin temperature. And by using the coupled simulation of heat and radiate transfer in indoor environments, conducting the integrated simulation, not only core temperature, but core temperature and skin surface temperature, but also the non-uniformity of skin surface of human body can analyze. And sorry, this is not the latest version. Sorry, but this is the in my understanding, in order to analyze the impact of inhalation exposure, inner surface or surface boundary conditions, setting of boundary conditions is critically important, especially between indoor environments and tissue or skin surfaces. I mean, for example, the objectives of PBPK model is to analyze some health impact, and some regulation model is. Sorry. No. And some regulation model is for analyzing the summer sensation or summer comfort, something like that. But both two models can provide the detailed information about the equilibrium surface temperature or equilibrium concentration. And these surface. Oh, thanks so much, Kyo. No problem. Sorry. No problem. And this can PBPK model and also this summer regulation model might be appropriate method to provide wall surface boundary conditions between human and indoor environments. I would like to say again, generally we usually use the commercial code, ANSYS fluent, something like that. Therefore, we must carefully set the boundary condition. This will be essential because the other technique is so sophisticated in commercial code. And remaining very important problem will be how to exactly set the wall surface boundary conditions in coupled simulation. From here, I would like to show some representative our simulation results. And this is a result of the some regulatory analysis. This one is also red color, uniformly distributed, but this is the result of the core temperature analysis inside deeper side in human body. And this is the skin surface temperature distributions under the displacement ventilation conditions. Therefore, relatively low temperature air is supplied from this side, and then you can see some relatively low skin surface temperature around here. And this core temperature information is feedback to the mucous heat and mass transfer model to analyze the skin surface temperature distribution in respiratory tract. And here, this is the main topic of my today's talk. This is one of the representative results for targeting e-cigarette smoking. And this is collaborated with CDPH in the United States. And in this analysis, we reproduce the e-cigarette smoking. And here, I would like to show the representative two results for inhalation exposure of formaldehyde generated from the e-cigarette devices, e-cigarette smoking, and also the acetaldehyde inhalation exposure. This is called as the first-hand exposure analysis. And in this analysis, the PBPK model is integrated into as the wall surface boundary condition in this respiratory tract model. And this is one of the results of the PBPK analysis. In order to integrate the PBPK model into this respiratory tract model, we can analyze the concentration profile inside tissue of respiratory tract. And this is a result of exposure budget analysis. And I would like to show this one is the formaldehyde result, and this is the result for targeting acetaldehyde. And for the total amount of inhalation of formaldehyde by way of the e-cigarette smoking, the total amount of absorption on the wall surfaces of this airway model is 39%. The completely different value of the previous I reported one, because this one is used the PBPK model as a wall surface boundary conditions. And the previous result is just we adopted the perfect sink condition, zero surface concentration. And the surface concentration is strong impact on the results of these types of simulation. And in this analysis, 11% of inhaled formaldehyde are estimated to be exhaled. And this is new emission source of contaminant in indoor environments. And in case of the acetaldehyde, as compared to the results of formaldehyde, the 23% of inhaled acetaldehyde by way of the e-cigarette device is estimated to be exhaled. And this is the two times differences. And this is the result of the PBPK integrated simulation. And I'm graduated from the Department of Architecture. Therefore, basically, I'm an architect, and I'm very interested in the indoor environmental quality. And our objectives to develop these types of human model is to use as a sensor to optimize the indoor environmental quality. And this is just 3 representative cases of exhalation of the passive smoking analysis. And you can see this is the there are 3 different ventilation systems, and ventilation condition and ventilation system has also strong impact on the dispersion or diffusion phenomena in enclosed space. And this is also the second-hand exposure analysis. This one is, in this analysis, we focused on the nicotine dispersion. And here is the smoker, and here is the passive smoker. And by using the PBPK analysis of the dermal exposure, we can analyze the nicotine intrusion by way of the skin surface. But the diffusion coefficient at the stratum layer is extremely small. This means the diffusion resistance is very large, and then the adsorbed nicotine is not effectively transported into the deeper side of the skin. It's just defensed by the skin surface. And this is my last slide, and I would like to conclude. The overarching objective of our study is to develop an in silico human model for indoor environmental design. And I have several simple questions. The physiological mechanisms of human body is so complicated. And furthermore, the interaction between indoor environment and human body is also so very complicated. And therefore, we must adopt the procedure to modeling each individual element, and then eventually integrate into some physiological model. And in my understanding, the verification or validation of numerical modeling or simulation results is very critically important. But as for the individual elements, of course, we have some possibility. I'm not sure, probability. I'm not sure in English, but we must have some choice to validate directly over numerical model. But I suppose the total human body is so complicated and very difficult to set the reasonable validation procedure of the simulation outcomes. Furthermore, I'm facing the very fundamental simple question: can we reproduce the complicated human physiological system by integrating the individual elements? And maybe this is essential and critical question for me, but unfortunately now I have no idea. And then here I would like to emphasize the importance of verification and validation of our numerical simulation. Thank you very much.